Hello everyone, and welcome back. Today we're going to continue our exploration of infinite series and consider what is called the power series of functions, and one can also consider power series of general relations that need not be univariate. So let's just go over a couple basics that we talked about last time when we first introduced the fundamentals of infinite series. In particular, infinite series are series that continue on forever, i.e. they have infinitely many terms. Some of the most common infinite series that we talked about were, for example, the geometric series, which is given by the sum from k is equal to 0 to infinity of x to the k, and we established that this infinite series converges to a finite element, in particular 1 over 1 minus x, as long as the absolute value of that element number x is between 0 and 1, non-exclusive of those boundaries. And we discussed a very similar series, which instead of looking at monomial terms, would look at reciprocal terms, which some people refer to as a p-series or a zeta series. And we say that this series converges to zeta p, provided that p is strictly greater than 1. And we also discussed a more broader class of series known as alternating series, which are series or infinite series that have this negative 1 to the power of k. That is, it switches from positive, negative, positive, negative, positive, negative terms infinitely many times. So we say that this converges to some number L, and in particular this number needs to be finite, provided that that sequence, ak, not including that alternating term, is positive almost everywhere. That is, there exists only a finite countable number of terms for which it is positive, and the limit of that sequence is equal to 0. Combining those two things, you have a eventually non-negative monotonic decreasing sequence, right? So that's pretty much what we have here in terms of the three fundamental infinite series that we definitely should be aware of. So what we're going to be looking at today is the following question. Is it possible that non-polynomial functions, for example, e to the x, sine x, hyperbolic tangent, and so on, can be represented as polynomials, and I'm going to put this in quotes, of infinite degree, i.e. infinite series. And when I say infinite series or polynomials of infinite degree, and the reason I put that in quotes is because polynomials are typically defined as going up to some finite number, what we're typically referring to is at least two different variations or options in terms of this representation. The first representation that some people consider is representing that function f of x in the form the sum from k is equal to 0 to infinity of some number ak times x to the power of k. That is, it looks like, for example, a0 plus a1x plus a2x squared plus a3x cubed, and so on, all the way up to anxn, and infinitely many more terms thereafter. So it sort of looks like a polynomial, but it continues on forever. So that's one variation of expressions that we're going to be looking for. And another representation, so this is a different representation, you can represent it as the sum from k is equal to 0 to infinity of some other numbers bk, and then x minus c to the power of k. Here c is going to be some fixed constant. So this is going to look like, again, b0 plus a1 x minus c, and this is supposed to be b1, and then b2 x minus c squared plus b3 x minus c cubed, and that's going to continue infinitely outwards, right? So these are both polynomial series because in some sense we can expand this b1 into that little first degree monomial term or binomial term. We can expand that and then distribute that b2 in it. We can expand that cubic and distribute that b3 in it. And we could in some sense rearrange and combine like terms and represent it in this first form. But there are some advantages and disadvantages of each of these, but in some sense one can be written in the form of another. So they're both what we call power series of functions, but they have different structure, right? So we say that this first structure is centered, or what we say centered, about x is equal to 0. Because notice in this particular term, x minus 0 to the power of k is the same as x to the power of k, whereas this term sort of tells us that this power series is centered about x is equal to c, where c is some fixed number, can be positive, negative, and of course if it's 0 it's equal to this first particular case that we have above. So let's look at some very trivial power series of functions, in particular polynomial functions. This isn't going to be too exciting, but it's going to sort of get you in the idea of what we're actually going to be looking for. So let's assume that we have the function f of x is equal to 5x squared minus 3x plus 8, and let's assume that we want to represent this function as a power series centered at x is equal to 0. So we want to represent a polynomial as a polynomial. So that's actually pretty trivial, right? So we can represent f of x, and usually we do it in ascending order, so degree 0, degree 1, degree 2, degree 3, and increasing. So we're going to have our constant term first, and then we're going to have our minus 3 times x to the power of 1, plus 5 times x to the power of 2, but this needs to be an infinite series, so we have to include our cubic term, our quartic term, our quintic term, and so on. So what would those coefficients be? Well, those aren't existent, so that means those coefficients must be equal to 0. So we have x cubed, x4, x5, and that is our infinite series for that particular polynomial. So we can say that, for example, our function, f of x, is equal to the sum from k is equal to 0 to infinity of akx to the k, where a0 is equal to 8, a1 is equal to minus 3, a2 is equal to 5, and ak is equal to 0 for all k bigger than or equal to 3. So I guess you could create a nice cute little function to represent 8 minus 3, 5, and 0 for all k bigger than or equal to 3, but I can just list them out since it's a relatively small set. Now instead of centering at 0, let's do something a little bit less trivial, and let's center it at about another point. So let's consider a power series. So centered about, let's do something easy. I'm going to say x is equal to 1. So that means we want our function f of x, which keep in mind was 5x squared minus 3x plus 8. We want to represent this in the form, the sum from k is equal to 0 to infinity of some sequence of constants ak times x minus 1 to the power of k. Keep in mind we only have a degree 2, therefore we only need to take k up to 2, right? So we only need up to k is equal to 2. So we need to expand that general form, and then we can equate coefficients to the left-hand side to sort of see what that a0, a1, and a2 should be equal to. Right? So let's actually look at what that looks like. So we have the sum from k is equal to 0, let's just go up to 2, of ak x minus 1 to the power of k. So that's going to be equal to a0 times x minus 1 to the power of 0, plus x1 times x minus 1 to the power of 1, and then a2 times x minus 1 to the power of 2. So that's the first three terms, which we usually call the second order representation of that infinite series. So we can write this as just, well, anything to the power of 0 is equal to 1 as long as x is not equal to 1 in this particular case, unless you want to conditionally define that. So we're just going to have a0 plus, and then we can distribute that a1 in, so we're going to have a1x minus a1, and then we can expand that, so it's going to be a2 times x squared minus 2x plus 1, for which we can then distribute. So we're going to have a0 plus a1x minus a1 plus a2x squared minus 2a2x plus a2, right? So that is our expansion, and we want this to be equal to our function, which was 5x squared minus 3x plus 8. So the next thing that I want to do is I want to combine like terms on the left-hand side of this expression and then equate coefficients of like powers. So for example, let's look at our x squared term. So I can write that as a2x squared, and then I want to look at my linear term, so it's going to be a1x and then minus 2a2x. So it's going to be plus a1 minus 2a2x. And then we're going to look at our constant terms, which are just a0 minus a1 plus a2. So that's going to be equal to plus a0 minus a1 plus a2. And all of that must be equal to 5x squared minus 3x plus 8. So we have a systems of equations here. We have three unknowns, a0, a1, a2, and actually three equations because a2 must be equal to 5. This expression must be equal to minus 3, and this expression must be equal to 8, and that's in particular a triangular systems of equations which we can easily solve. Right? So we have that a2 must be equal to 5, which means that a1 minus 2a2 must be equal to minus 3 on the right-hand side, which means that a1 minus 10 must be equal to minus 3, which means a1 must be equal to minus 3 plus 10, which is equal to 7, so that's our next coefficient. And then we look at our last coefficient, which is going to be a0 minus a1 plus a2 must be equal to positive 8 on the right-hand side, which is going to imply that a0 is going to be equal to 8, and so over here we have minus 7 plus 5, which is minus 2, so we're just going to add 2 to that, so we're just going to have 10 there, right? So once we have that, then we have that our function f of x, which eventually or originally was 5x squared minus 3x plus 8, can now be represented as the infinite series, the sum from k is equal to 0 to infinity, of akx minus 1 to the power of k, where a0 is equal to 10, a1 is equal to 7, a2 is equal to 5, and ak is equal to 0 for k is greater than or equal to 3. And that's how we can find power series representations of polynomial functions centered about any real number. So now we know how to represent polynomials as power series centered about any real number c. But obviously those examples are sort of trivial, but what about non-polynomial functions? To start, let's consider the very nice function f of x is equal to e to the x. Our goal is to represent this function e to the x as a power series, which is in some sense an infinite degree polynomial. In particular, it's going to be of the form the sum from k is equal to 0 to infinity of some sequence of numbers ak times x to the power of k. So let's assume we want to find the power series of e to the x centered around 0. Some people refer to that as a Taylor series or a MacLaurin series, depending on the literature, but I'm just going to call it a power series centered around 0. So what this series looks like is going to be equal to a0 plus a1x plus a2x squared plus a3x cubed, and so on. So we just need to find these numbers a0, a1, a2, a3, hopefully a pretty rule that we can sort of compactify so we can get any coefficient that we want by just substituting the value of k, and then seeing what we have. So notice that every term in this infinite series has x except for that particular expression. So if we substitute x for 0 into this expression, we actually can find exactly what a0 should be equal to. So when x is equal to 0, we have that e to the x, when x is equal to 0, is just going to be equal to e to the 0, which is equal to 1. And 1 is going to be equal to a0 plus 0 plus 0 plus 0, and so on. And notice that a0 plus a bunch of zeros is just a0, so we have that a0 must be equal to 1. So we have our very first constant figured out for us. So that means we have that e to the x must be equal to 1 plus a1x plus a2x squared plus a3x cubed, and so on. So now that we know what a0 is, how are we going to find a1, a2, a3, and every single constant in this expression? So we already know that e to the x is easily differentiable because it is its own derivative. So what I want to do is I want to just differentiate this function e to the x on both sides of this expression. Because we're assuming that this is equal to this, we just need to figure out, okay, what those coefficients are to make that true. So we're just going to take the derivative of 1 plus a1x plus a2x squared plus a3x cubed, and so on. And we're also assuming that this series converges for whatever x value we're going to substitute. Keep in mind, regardless of what the value of a0 was, that's going to differentiate to 0, which is actually pretty nice. The derivative of e to the x is itself, so we're going to have e to the x is equal to a1 plus 2a2x plus 3a3x squared plus 4a4x cubed, and so on. So keep in mind, this is again e to the x is equal to some expression, and every expression after that leading constant term is going to have an x in it, so we can just substitute 0 into this expression and figure out what a1 is equal to. So again, e to the 0 is going to be equal to 1, and 1 is going to be equal to a1 plus 0 plus 0 plus 0 plus and so on. So from this expression we can get that a1 also is equal to 1, but it's actually not the same one as the first. And if you don't know what I mean by that, you'll see in just a moment. So let's look at our series now. So we have that e to the x is equal to 1 plus x plus something x squared plus something x cubed plus something x4, and so on. And we differentiated e to the x one time, and we got x plus 2a2x plus 3a3x squared plus 4a4x cubed, and so on, in order to get that a1. And now what I want to do is I want to differentiate, and also that should be 1, not x. And now we're going to differentiate and figure out what that a2 is going to be equal to. So once we differentiate this again, it's going to still be e to the x, and that's going to be equal to, now notice that the coefficient of x is 2a2, and then over here we're going to have 3 times 2a3 plus 4 times 3a4. And then the next term is going to be equal to, let's not forget our x's, so x squared, and then 5 times 4, a5x cubed, and so on, right? Okay, so what does that mean? So when x is equal to 0, we're going to have 1 is equal to 2a2 plus a bunch of zeros, which means that a2 is equal to 1/2. Right? So now we have a change in our pattern. Now let's take this expression and differentiate it again. So we're going to have e to the x is equal to, so that disappears. We're going to have 3 times 2a3 plus 4 times 3 times 2 a4x plus 5 times 4 times 3 a5x squared plus and so on. We're going to substitute 0 into this expression again, so x any e to the 0 is going to be 1, is going to be equal to 3 times 2. I'm going to put a 1 there, even though it's not really efficient. And then we're going to have a bunch of zeros here. So 0, 0, 0, because we have an x in every single term. So what we have here from this expression is a3 is equal to 1 divided by 3 factorial. And if you notice that 1 over 2 is the same as 1 over 2 factorial, a to the 1 was equal to 1, which is the same as 1 over 1 factorial, and a to the 0 was also equal to 1, which is the same as 1 over 0 factorial. So we're like, okay, obviously we see a pattern, and if you know mathematical induction, you should be able to prove that this actually exist for all these series. So one can prove that ak is actually equal to 1 over k factorial, right? Which is actually pretty nice. So that means what? So that means e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x4 over 4 factorial, and so on. And this is the power series of e to the x centered around x equals 0, which is actually pretty nice. And some people will just remember this in power series form, x to the k over k factorial, right? And that is a very important result. So what can we do with this, at least from the analytical perspective? And keep in mind, we're assuming that this series does converge for all x in the set of real numbers. So if I were to look at the infinite series, let's look at a nice little example. Let's assume that we have the sum from k is equal to 0 to infinity of 2 to the k over k factorial. Does this series converge or not? In particular, this is going to be equal to 1 plus 2 squared over 2 factorial plus 2 cubed over 3 factorial plus 2 to the 4 over 4 factorial plus and so on. Notice that these terms are getting bigger, but as k goes to infinity, the factorial is going to dominate that exponential on top. So these terms, although the sum is getting bigger, the terms themselves are getting smaller, right? So do they get smaller fast enough for this to converge? The answer is yes, and I'm going to go ahead and prove that. So if we look at this, what actually does this converge to? Well, this is precisely equal to the Taylor series, or the power series, of e to the x, which is just going to be equal to x to the k over k factorial, when this is evaluated at x is equal to 2, and we know that that infinite series is precisely equal to e to the x when x is equal to 2, which means that the exact value of this series is actually equal to e squared. Now, what can you use this for? Well, do you know what e squared actually is equal to? Maybe not, unless you use a calculator. But e squared exactly is equal to 1 plus 2 squared over 2 factorial plus 2 cubed over 3 factorial plus 2 to the 4th over 4 factorial plus and so on. And let's assume that we want to get an approximation for this. So if we want to approximate this, we can say, okay, this is 1 plus 2 squared over 2 factorial plus 2 cubed over 3 factorial plus 2 to the 4 over 4 factorial, right? So this is our fourth order approximation, because we're taking up to the k is equal to 4 term for this particular series. Now, you might not know what e squared is equal to, but you should know what each of these terms are equal to. That's going to be 1 plus 2 plus 4 over 2 plus 8 over 6 plus 16 over 24. And all those are very nice numbers, and one can show that that is actually equal to 7. So we have that e squared is approximately equal to 7, at least from the fourth order approximation term. And in case you're curious of what the exact value is, it's approximately equal to 7.389056. So if we wanted a better approximation, we just take, for example, several more terms, 5th, 6th, 7th, 8th, 9th, 10th order approximation, and the convergence is going to get better and better and better in terms of the approximation, right? But keep in mind, even though we have not proved it, it requires a little bit more rigor that I want to get into today, but e to the sum from k is equal to 0 to infinity of x to the k over k factorial converges to e to the x for all fixed values x in the set of real numbers, right? And we, in some sense, indirectly prove that by deriving what those coefficients would be if this were to have converged in the first place. Now that we know how to find the power series representation for e to the x, you probably would try and find, for example, the power series representation for other functions using similar algebraic trickery that we applied for the e to the x function. In particular, one important power series representation is that of sine x. So again, what we seek is a representation of the form the sum from k is equal to 0 to infinity of a subscript k times x to the power of k. And we just need to figure out what those coefficients ak are. Again, it has the same structure as before, a0 plus a1x plus a2x squared plus a3x cubed, and so on. So, if we want to go ahead and try and find the power series of sine x since about x is equal to 0, a good starting point is, substituting x for 0. Because we know the sine of 0 is equal to 0, and that's going to be equal to a0 plus a bunch of zeros. So from this expression we see that a0 is equal to 0. So this power series doesn't even have a constant term. And that's actually pretty interesting because our e to the x one did. And I leave it as an exercise to actually show that all coefficients ak is equal to 0 if k is even, right? So if this is true, then that means the power series of sine x just looks like a1x plus a3x cubed plus a5x to the 5th plus a7 x to the seventh, and so on. So if that is the case, well, we would have to figure out what those a1, a3, a5, a7 are. So for example, if we take the derivative of sine x, we get cosine of x, and we have cosine of x is going to be equal to a1 plus 3a3x squared plus 5a5x4 plus 7a7x6, and so on. And if we evaluate, for example, cosine of 0, which we know is equal to 1, we have that a1 is equal to 1, and now we have our first non-zero coefficient. And we can see that we're going to get a 3 factorial from here, a 5 factorial from here, a 7 factorial from here, and in particular this is a 1 factorial for our a1 term. So once we combine all these algebraic results, once you convince yourself that they actually are true, what we're going to have is that the power series of sine x centered around x is equal to 0 is given by x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial plus minus and so on. In particular, we can represent this in infinite series form as sine of x is equal to the sum from k is equal to 0 to infinity of negative 1 to the power of k, which starts on positive 1, then goes to negative, then goes to positive. And then we're going to have all odd powers of x that start at 1, so that's going to be 2k plus 1. And then we're going to have the same exact value on the bottom in the factorial. So we're going to have 2k plus 1, the quantity factorial, right? So that is the power series of sine centered around x is equal to 0. Similarly, you can also derive the power series for cosine. So cosine is going to have a similar result. You can probably take the derivative of this power series for sine to get the power series for cosine. That's also a fun little exercise. And you're going to have the sum from 0, 0 to infinity of negative 1 to the power of k of x to the 2k even over 2k the quantity factorial. And that would be the power series representation for cosine. Similarly, if you know anything about hyperbolic trigonometric functions, in particular hyperbolic sine of x, which is equal to e to the x minus e to the minus x, all divided by 2, and hyperbolic cosine, which is e to the x plus e to the minus x over 2. From both of these expressions, you should be able to see that the hyperbolic sine of 0 will be equal to 0, and the hyperbolic cosine of 0 will be equal to 1. Once you have these results and you know about the derivatives of hyperbolic sine and cosine, then you should be able to derive the power series representations for these two functions as well. In particular, the power series for hyperbolic sine centered around 0 will be equal to the sum from k is equal to 0 to infinity. It's going to be practically the same thing as sine, except the alternating term. So we're going to have 2k plus 1 all over 2k plus 1, the quantity factorial. And we're going to have that hyperbolic cosine of x will be equal to the sum from k is equal to 0 to infinity of x to the 2k all over 2k factorial. And those would be the power series for hyperbolic sine and hyperbolic cosine, both centered around 0. And using a little bit more messy algebra, you can also find these representations for these functions centered around other points. For example, 1, 2, 3, pi over 2, provided that that point is actually in the domain of that function. The next power series representation that I want to derive can actually be derived from other infinite series that we've already established. So if we call the geometric series from last time, which is the sum of the whole number powers from 0 to infinity of x, then we know that this converges to 1 over 1 minus x as long as the absolute value of that x is in between 0 and 1. So what we can do is we can actually take the integral of both sides of this expression, and we're actually going to get another infinite series, right? Because the integral of an infinite series is also an infinite series. So once we do that, and let's assume we're going to just do the indefinite integral. So the indefinite integral of 1 plus x squared and so on. Let's integrate with respect to x. That's going to be equal to the integral of 1 over 1 minus x dx. So on the left-hand side, we can use the power rule, which is actually pretty easy. So we're going to have x plus 1/2 x squared plus 1/3 x cubed all the way out to some arbitrarily large term. And let's put the arbitrary constant on the right-hand side just to keep things nice. And on the right-hand side, that's going to be equal to -1 times the natural log of 1 minus x. It's either you can verify that directly by differentiation or use u substitution if that makes you feel any better. And let's not forget our lonely constant c. So what exactly is this particular constant c equal to? Well, the first thing that we have here is a function on the right-hand side and an infinite series on the left-hand side. So we can actually represent that, and technically we can call that, for example, c1. I'm going to negate it and call it c later. So what we have here is that the natural log of 1 minus x is going to be equal to negative x plus 1/2 x squared, and we can technically put that as 1 over 1, and then 1/3 x cubed plus so on, plus some other constant c, where c is just the opposite of c1. So we can write that instead as the natural log of 1 minus x is equal to the negative infinite series from k is equal to 1 to infinity of x to the k over k. Not k factorial, it's not equal to e to the x, it's just equal to k. It grows a little bit slower than the exponential function, right? And then we're going to have this plus c term. So what is this c equal to? So we practically have an infinite series representation or power series representation for the natural log of 1 minus x, but what is that c equal to? Well, if x is equal to 0, we're going to have the natural log of 1 minus 0, which is the natural log of 1, is equal to negative the sum from k is equal to 1 to infinity of 0 to the k divided by k. We know 0 to the power of k is going to be equal to 0 for all values, so we're going to have 0 is equal to 0 plus c, which means that constant c is just going to be equal to 0, so that constant is irrelevant for us. So therefore, a power series representation for the function 1 minus x is just going to be equal to -1 times the sum from k is equal to 1 to infinity of x to the k divided by k, but it doesn't converge for all k, and keep in mind that this is centered around x is equal to 0. This only converges for x is in -1 to 1, except for 0. And notice that this is a power series centered at x is equal to 0. Right? So what can we use this particular expression for? So keep in mind this expression only works for x's between -1 and 1, not including 0. So therefore we can approximate this or use it to approximate, for example, the natural log of, I don't know, let's do 1 minus 1/2. Because we know that 1/2 is in between -1 and 1, except for 0. Therefore, the natural log of 1 minus 1/2, which is just the natural log of 1/2, is going to be equal to exactly -1 times the sum from k is equal to 1 to infinity of x, which is now taking the form of 2. So we're going to have 2 to the power of k, and then k on the bottom, and then we're just going to have 1 on top. And this is actually going to give us an approximation for the natural log of 1/2, which is actually pretty nice. We have an always positive term on the right-hand side that's going to negate it, and the natural log of any number between 0 and 1 is also a negative number as well, so that at least the sign checks out, and at least this number satisfies the interval of convergence. But you cannot just use any random x value. For example, if I want to figure out what is the natural log of 5, for example, which is just the natural log of 1 minus -4. Keep in mind, -4 does not belong to the region of convergence for this power series, so you cannot say that this is equal to -1 times the sum from k is equal to 1 to infinity of -4 to the power of k over k. It doesn't work that way. In particular, you can look at this series and you can be like, oh, well, this is actually a pretty interesting series. That's just going to be equal to -1 times the sum from k is equal to 1 to infinity of -1 to the power of k of 4 to the k divided by k. And you're like, well, that's an alternating series. Does this series even converge? Well, notice that exponential functions grow faster than linear functions. Therefore, this is not a decreasing sequence. Therefore, this does not converge by the alternating series test, right? Now, could it converge by other tests? We haven't established that. But at least the alternating series test fails when it comes to the convergence of that series, which is definitely a bad sign. But at least in that sense, we see that the natural log of 5 cannot be approximated by this infinite series, which is definitely a downside. The last thing that I want to do today to close out this discussion on power series for functions is just give a graphical demonstration of what power series for functions is actually doing and what we mean by in terms of convergence and divergence of these particular series. So what we're going to do is we're just going to do a 20th order approximation, for example, for sine, because we already have derived the power series representation for that function. So let's go up to 20 for this expression, and the function that we're going to be interested in is f of x is equal to the sine of x. So the Taylor series, or the power series representation for sine centered around x is equal to 0, is going to be equal to the sum from k is equal to 0 up to this power of n. So this is the nth order power series approximation for f centered about 0, or just you can just say the Taylor series for that function. And that's going to be equal to -1 to the power of k times that power expression, which is just going to be equal to x to the 2k plus 1 over 2k plus 1 the quantity factorial. So 2k plus 1 the quantity factorial. Right? So if you notice here that this function in green actually lines up exactly well with that blue. But it's actually not as good as it may appear, because if we zoom out, eventually this function actually does not match our particular curve. And notice that it actually converges pretty well on the interval, say, -15 to 15. And in particular, this is a symmetric approximation, because the order is actually super large. But if we actually decrease this order down, for example, to order 3 power series, notice that the approximation is actually very, very weak if we step outside of the interval -3 to 3. Now, the difference between these functions, for example, f of x minus t, f of x for a particular value, for example, we can do x is equal to 2, right, is 0.000. So if we look at x is equal to 2 in this particular picture, the difference between these curves, blue and green, is actually very small, even if we're only doing an order 3 approximation. And obviously, if we just do a quadratic approximation, notice the difference is a little bit more bigger. Order 3's approximation is, of course, better. Order 4 is an approximation, but of course, just because it's good at x is equal to 2, it's going to be worse as you get farther from the point for which this series is centered at, which is centered at x is equal to 0. So the farther you are from the center of this power series, the worse the approximation is going to be, regardless of the order for which you're using, assuming that you are using an nth, a finite order approximation for that power series representation. But keep in mind, this function sine of x actually is going to converge for all x. So if you want this series to converge good for x is equal to 25, as long as your series is high enough, you should be able to get whatever accuracy you desire, as long as your order is high enough. And there is some numerical theory associated to that, which we'll dive into at another time, right? But not all series converge for all values x in their domain. We discussed an example of the natural log of 1 minus x, for example. So let's actually take a look at that. So if we look at, for example, a third order approximation for the function, let's look at the function g of x is equal to the natural log of 1 minus x, because we actually derived an approximation or power series representation for this function, but it didn't converge for all real values x inside of its domain. So what was the power series representation for this function g? So that came out to -1 times the sum from k is equal to 1 to, let's go up to n for this approximation. And that power series representation was x to the k divided by just k. Right? So if we notice that as x gets close to 0, it's actually a pretty decent approximation, but as x gets farther from 0, obviously it gets worse and worse. But of course, if we increase this order from, say, n is equal to 3 to n is equal to 10, obviously it gets closer to this curve on a larger interval. But notice, even if I make it n is equal to 20, or even n is equal to 50, notice it practically doesn't get any better outside of this little window from -1 to 1, right? So keep in mind, x is equal to -1 is over here, and x is equal to +1 is over here. Regardless of the order, this power series approximation will not converge to this function g outside of this interval of convergence, regardless of how high that order is you're using. And that's why it's very important when you're actually deriving and analyzing these power series that you actually know the interval of their convergence. For this example, it was x between -1 and 1, and 0 of course can be conditionally defined as 0 if you want to define it as so, right? So those are the fundamentals associated to the power series of elementary functions, which you definitely should understand, because a lot of functions are very difficult to analyze, at least analytically, in terms of integration and differential equations. So power series gives a very useful tool in analyzing those otherwise complicated and hard to deal with functions. So I hope you enjoyed this video, and I'll see you in the next one. Take care.